Well, I don't have that much prepared, so I'm going to ramble. This is a ramble day. So, but you're probably thinking, if this is a ramble day, what are all the other days? Well, they're also ramble days, but we'll see how far we get. Okay, so we're talking about the probability transition matrix, and we introduced this last time. We wrote this as P equals D inverse A. And so, as you recall, A is our adjacency matrix. D inverse is 1 over our degrees. And we're dealing with very simple random walks in the sense that the kind of random walks we're going to deal with are ones where essentially we can go in both directions. So if we start with our paw graph, we're really thinking of it as between each edge, you can go either way. Now, you kind of have to pay a little bit of attention when we're talking about your asymmetry. In other words, what goes where. So when we talk about P sub ij, joining vertex I to vertex j, this is your probability of going from I to j. And even in the case of graphs, even where we're allowed to reverse, this is not symmetric. But we saw last time that this is similar to a symmetric matrix. So real eigenvalues, that's good. Now at the end of last time, we didn't fully finish this. So that's where I want to start, is we were talking about our eigenvectors. And, but in particular, well, we weren't talking about eigenvectors, but we kind of were. We just didn't realize it yet. We were talking about our, what is it called, probability state. And I'm missing a word, but that's okay. I'll remember it later in our discussion. So this is, we assign our probabilities to our vector, our vertices, excuse me, and the probability, I'll say P sub v, that's the probability of being at vertex v, it's greater than or equal to 0. And the sum over all vertices of the probability is 1. And so we said, okay. So when we think about random walks, we're moving. So we can't really say, okay, I take a random walk, where am I? That doesn't make sense. But what we can say is, I take a random walk, how likely am I to be in a particular location? That's a good question. And that's the kind of question that we're asking. And so the claim is, if we take one of our probability distributions, and we write this as a row vector. So probability at vertex 1, probability at vertex 2, probability at vertex n. Then if we take one step in our random walk, this is f times p. So the new probability distribution after taking one step. So in other words, what's happened? Well, how do we actually compute that? So I want to make sure we can convince ourselves that this is true. And because we write it down, but it's like, well, is it really true? So how can we think about that? Well, let's think about what's the probability that we're at vertex. And I notice I've been using i's and j's, but I'm going to go back to, say, u, after one step. So suppose I wanted to compute that probability. Okay, so how would one do that? Well, I have to get to vertex u. So what am I going to sum over? Right, yeah. So everything that I could, so I'm going to sum over all the vertices where I can take a step. So sum of all vertices such that there's a directed edge from V to U. Now this here, what we're doing right now is not dependent on the underlying graph being undirected. This is just a general statement. Okay, so now we have to come up with better notation, and so we're going to call this side P sub u. Let's put a hat on it. Just, I don't want to use primes because then I'll think I'm taking derivatives and I'll get in trouble. So what do we do? Well, we say, okay, we have to say what's the probability that we're at vertex v. All right, that's P sub v. And now, what's the probability that we actually transition from v to u?
Well, you could do this with like a hypergraph, right? So you could have multiple edges from v to u. So
Ooh.
The number of ways to u, the total number of out edges.
Right. Well, I think you said hypergraph, but you can think of things like multigraph. Hypergraphs are kind of strange with random walks because you have to think about what is it. So a hypergraph, for those who don't like to think about such things, are it's another way to think about a generalization of a graph, where the edges now are sets instead of just sort of like thinking as oftentimes when we think of an edge, it's like, oh, there's a line. But edges are sets. Well, they always have been sets. Yeah, but now they're like bigger sets. So they're some subset of the vertices. So it could have like 3 vertices in one edge. And then the question becomes, okay, well, how do you figure out what does it mean to take a random walk on that edge? The nice thing is when there's only 2, it's like, well, there's 2 vertices and I'm at one of them. So the random walk says go to the other one. If there's many vertices, it's like, well, pick one. Maybe. There are just other ways you can define it. Yeah, right. You can do all sorts of things. Sure. And okay, so it's PV, and then it's the probability that you transition from V to U. And so we actually have a way to talk about that. That's back in our matrix P. So, and now you'll see why my uppercase P's and my lowercase p's look really similar, and I apologize for that, but PUV. So this right here is, oops, sorry, I wrote PV, it's PVU, because we want to go from V to U. So probability of transitioning from V to U. And this is our, again, this is our matrix P that we have this P equals D inverse A, but in general for a random walk, that we can talk about for general graphs, directed graphs. And now we think about, okay, well, what's going on here?
U is fixed is like the column.
Right, exactly. U is fixed. It's a column. And so when you think about this in terms of a matrix multiplication, if here's your P, you have your uth column. And then you're going down here. You say, okay, well, if I'm thinking about this in terms of multiplication, well, if I want to do a column, then the best way the way that works is if I do a row in the front. And that's why we do a row vector in front of P. So it's P1 times P1U, P2, P2U, so forth and so on. And so now we say, okay. So entry by entry, what we see is, we say, all right, well, this is really our, so if we let F be our probability transition matrix, so this is F times P, and then we're reading off the uth entry. And so that's the justification for how we say we can go from what's our current distribution, our current probability distribution, to our next probability distribution. And we just say, okay, we turn the crank, multiply by P. Good. Now, we know a couple of things. As from last time, we talked about we understand our eigenvalues. They're fairly tame by our standards. There's nothing too unusual. Let's talk about our largest eigenvalue. So if we assume we're ergodic, all right, pop quiz, we talked about ergodic last time. What's ergodic mean? Aperiodic and connected. And connected means irreducible, yeah. So another way to say ergodic is it's good mixing. So that our graph mixes. And we said, okay, so we know that in that case, because I can take FP times all, if I take P times all 1, we get back all 1s, which is just to say, if I'm at some state, I do something. That's what that statement means. Because if you add up the rows, it just says, okay, what's the probability that you transition to somewhere? And so, well, the probability you transition to somewhere in a random walk is 100%, because that's what random walks do, you transition. So now we have another question, which is to say, okay, what's the right eigenvector for the left-hand side? Because P is not symmetric. When P is not symmetric, if you have a right eigenvector, you'll have a left eigenvector, but they need not be the same. So now our question, our query, the left eigenvector of P. And in particular, for the large eigenvalue, lambda equals 1. And I didn't say why we wanted to do ergodic, so as you quickly derive it in your head what that's going to look like, ergodic gives us that we have an eigenvalue at 1, and it's a simple eigenvalue, and all other eigenvalues are from -1 to +1, but we can't have an eigenvalue of -1. So all our other eigenvalues lie between -1 and +1 strictly. All right, so a left eigenvector. Cool. Well, can we say anything about this eigenvector that we're after? Based on my tone, exactly. Like Steve has already spotted something. What can we say about the entries of this left eigenvector?
Positive.
Because? And you are correct, that they are positive.
Is it because the right hand side also is positive?
Yes.
Yeah.
And so what do we know? When you have the largest eigenvalue in size, the eigenvector associated with it always has positive entries, if we're in our good mixing state.
Both left and right eigenvectors?
Yes, because you can just take transpose. We're balanced. We consider both sides of the matrix. Fair and balanced. All right. Well, what would we like it to be?
D, but in a column.
Cool. What would you like it to be? The eigenvector?
Yeah.
I would like it to be the all ones, but it's not.
Right. We'd like it to be the all one. So we're like, okay,
No.
can we get there?
Like just write the degrees of the vertices in a column.
Ooh.
Or in a row, whatever.
Ooh.
However we want to write this.
So you actually are, you're
Because basically you're just
yes.
doing that the inverse.
Right. So yeah. So the idea is like, boy, you know this, you know, if we didn't have that D inverse, so we just had A, then life is good, symmetric, all ones. So it's like, well, okay, let's try something. I like how you said, let's undo that D inverse. So how does one undo that D inverse? Multiply by D, right? D inverse inverse. And then we'll do the all ones, and we'll put a transpose here just so it's clear. You know, usually I'm very lazy and I'll just say, from context we would understand that this is a row. But just in this context, we'll go out of our way. Now the question is, does it work? And I wrote something down, so that's probably a pretty good sign. So let's talk about what happens. First off, the D and the D inverse. That's something we can understand. What does that do? Yeah. So this becomes 1 transpose times A. Now here you're taking the row vectors and times A. So yeah, it's the sum of the columns.
A times 1 transpose because A is symmetrical.
Well, it is very similar to A times 1 trans. You know, you can say, if you do prefer that, you could say it's like A times 1 transpose. You subtly left out the parentheses when you said it out loud, but I could hear them.
Yeah.
I could hear the context. But, okay, still, what's going on? So now instead of column sums, we can think of row sums. What are we finding when you do row sums?
Oh, but that's
It's just the degrees.
It's the degrees. Yeah. So it's, degree 1, degree 2, down to degree n,
those.
Amazing.
transpose. But what's another way to write that matrix?
1 transpose D.
Unsettling,
Hmm?
One.
yeah. Okay, no, that's exactly what,
Yeah, that's exactly.
yeah, okay.
Well, my
D times 1.
it's D times the 1. And of course then taking the transpose, this is 1 transpose D. So all right, cool. So we found a left eigenvector, but it's not the one we want. It's almost the one we want. We want to make it even better. What can we do that makes it even better?
Divide by n.
Divide by n?
No.
Oh, maybe. I mean, it depends on the graph. But certainly, we automatically satisfy that the probabilities are greater than or equal to,
Yes.
you know.
The sum of the degrees.
Yeah. So the goal here is all entries are non-negative. They're actually all positive. And so if we want to turn it into some probability distribution, we say, well, if we could just make it so that the sums of the entries were 1. All right, so we sum the entries and then divide by that. And as you said, that's the sum of the degrees. So now we have this really cool, the bestest left eigenvector for the eigenvalue 1 is, as was said out loud, 1 over the sum of all the degrees times 1 transpose times D. All right, great. Exactly what you would think. Okay, so why is this the bestest? Well, now we'll talk about what's happening to our random walks, our distributions for our random walks. So start with any distribution. And I'll call it F. Now, what's true is that it's an it's a vector. And because of our matrix, it has nice eigenvalues. They're all real. It's similar to something which is symmetric. And that's diagonalizable. So our matrix is diagonalizable. So we have a full set of eigenvalues and eigenvectors. Well, we always have a full set of eigenvalues. The eigenvectors is the interesting one. So if I have any distribution F, then what's true is that F is C1 V1 plus C2 V2 plus Cn Vn, where V1, V2 up to Vn are the left eigenvectors of our matrix and P. Okay, and let's just assume that our first one, V1, is the one we just found. So that's our bestest one. All right. So, pop quiz. Lambda 1 equals 1, and lambda 2 up through lambda n are all, well, okay, we'll say lambda 1 equals 1, and negative 1 is less than lambda 2. I know what I want to write. And okay, negative 1 less than lambda 2, comma, dot, 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 comma, lambda n less than 1. So all the other eigenvalues are between negative 1 and 1. All right, that's what I wanted to write, and I succeeded. It only took me 3 times to write it. What happens if we take f times p? One step. What does that look like? Well, it's C1 V1 plus C2 V2 plus Cn Vn times P. So what do we do? Yeah. We can use the fact that linear algebra is linear. And so we get, well, V1, that's our nice eigenvector for 1, so that's just C1 V1. What happens with the rest of these?
C2 lambda 2
Right. All the way up to Cn lambda n Vn. Okay. So in other words, when you multiply by P, you add the corresponding lambdas to each piece. And this one just happened to have lambda equals 1. So that's one turn. What happens if we take, say, k turns? What will we look like?
Still C1 V1.
Yep, still C1 V1, good.
All the lambda's going to power k.
Yeah, so every time we take a step, we up our lambdas. All right, well, that's not so bad. That seems kind of reasonable. Okay, great. Well, now let k get big. In other words, we're letting k, think of it as many, 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 many steps. So k goes to infinity. What happens as k goes to infinity?
We're just left with C1 V1 because C2 through Cn, those are all have magnitude less than 1.
Yeah. Well, so the eigenvalues, because in absolute value, the eigenvalues are smaller than 1. That says all of this stuff goes to 0 in the long run. And so the only thing that doesn't go to 0 is the very first thing. And so we say, okay, so fp to the k converges to C1 V1. But actually, we know what C1 has to be if we start off with a probability distribution. Because if you have a probability distribution and you take one step, what do you have? You still have a probability distribution. So keep taking it over and over, you still have probability distributions. So we say, okay, so C1 has to be the right number to make it a probability distribution. So what's the right number?
Sum of the degrees. 1.
Well, we've already fixed V1 with the sum of the degrees. So the answer is, it actually has to be that C1 equals 1 to be a probability distribution. So it's converging to a probability distribution, and we know V1 is already a probability distribution. So anything that's a multiple of a probability distribution, where the multiple is not 1, won't work, because you can't get your sum equals 1. So this is our great aha. You'll often hear something called a stationary distribution. And what this is this is a distribution where when you take one step, one crank of the wheel, if you will, then you don't change. Your probability is the same as before. And now we say, well, we know what the stationary distribution is. Our stationary distribution is V1. So let's suppose we apply now our great knowledge to a graph. We'll do the PA graph. I claim we can compute the stationary distribution of the PA graph. All right. So, first off, what's our sum of degrees?
8.
8. Yeah, 2 plus 2 plus 3 plus 1. So, if I have a vertex of degree 2, then the stationary distribution says the probability that I'm at that vertex is, well, 2 over 8, which is 1/4. And it doesn't matter where you are in the graph, it just matters what your degree is. So the other vertex of degree 2 still has the same probability. How about at this central vertex? 3/8. And finally this lone sad vertex that doesn't want to hang out with a lot of friends. 1/8. I shouldn't say. There's nothing sad about hanging out with just one friend, if it's a good friend. All right. And so we say, all right, so there we go. So we have, this is what we have, the stationary distribution, and it's very easy to compute. Now, there's another comment that we can make. By the way, this is sort of intuitive. If you think about it, what does it say? It says, well, vertices that are well connected, you're more likely to go to, because there's lots of things that will transition into that. Whereas vertices that are relatively poorly connected will probably be lower, because there's not a lot of ways that you can get there. And so it matches with our intuition. And that's good when things match with our intuition. Okay. I don't have the time. How are we doing? We're doing fine. Cool. So, let's see. What are some other things we can say? We should definitely make this observation. So we are seeing that these go to 0. This sort of tail end of f times p to the k. And we're saying, okay, well that's because these powers of lambda go to 0. But now, there's sort of a question, how quickly do we converge? And so when we say, do we converge, we're saying we're doing a random walk, and we want to know, and how soon do we get close to the stationary distribution? So how quickly does a random walk converge to the stationary distribution? How can we answer that question? Does this question even make sense?
Is what we have up there the stationary distribution?
So the stationary distribution is V1, this vector.
Yeah.
And so now, of course, you might say, well, you could convert in no steps if you start in the stationary distribution. well, okay, all right, come on. When I want to like, what's like the worst case scenario? Like, how long would it take?
Is it going to depend mostly on lambda 2 and lambda n, like how close they are to -1 and 1?
Right, yeah. So the key here is to say, well, it's converging in some sense exponentially. And it really boils down, the C's, whatever, they're fixed. Whatever your initial C's are, they're going to stay the same C's. And so it depends upon our eigenvalues. And so we know we have that one eigenvalue of 1. And so the question is, where are the others? Well, so how quickly does it converge? And I like your answer is how, I feel like I'm answering a question with the question, but I'm still going to write it down. Now, how close are the non-1 eigenvalues to 0? And that's essentially the answer. So the closer your eigenvalues are, so if you're in a scenario where your eigenvalues are very close to 0, except for the big one, then that sends a signal like, that's going to converge very rapidly. On the other hand, you might say, well, what if you had something where it's like, all right, I have my eigenvalues, and I even have something very close to 1. It can't be like exactly 1, but maybe it's like 0.99, and I have them spread out. Well, it's the same number of eigenvalues, but now it takes some time. 0.99 to the n, yeah, it goes to 0, but it takes time. Yeah, how close are the non? Yeah, it looks like it says like non-negative 1. That's a non-1. Yeah, that's probably a better way to say it. So there's a philosophy that I'll mention several times, so I might as well mention it now, which says you can get a sense of how your graph behaves based upon how well things cluster around 0. So if things are very close to 0, that says, well, your random walk quickly converges. In other words, from our perspective of mixing, that says fairly rapidly things diffuse and they go to roughly the right area. Whereas when things don't have your eigenvalues clustered around 0, it takes longer. Well, that's usually a sign something's happening in your graph. Now you might be saying, okay, what's an example of something where you have your eigenvalues close to 0? Do we know an example of a graph where the eigenvalues are not going to be close to 0? Or in other words, a graph where the eigenvalue gets pretty close to 1. Now at this point you're probably saying, but Steve, we haven't done any eigenvalues for these weird matrices. I'll give you a hint. If our G is K regular, in other words, all vertices have the same degree K, then what does P look like? P.
1 over 2.
Yeah, because D inverse is constant on the diagonal, so you can pull it out, and it's a constant times the identity, so it's 1 over K times A. So you can quickly compute the eigenvalues. If you know how to compute the eigenvalues for the adjacency, and it's regular, then it's like, it's a freebie. You get the eigenvalues for your graph. There is actually another thing we can say. I don't know if we've talked about semi-regular. All right, no, is it semi-regular, biregular? What do you call a bipartite graph where all on one side it's 1 degree and all on the other side it's another degree? Okay, then we won't say the result yet. We'll have to wait till we... Okay, then we're calling it biregular. Okay, so G bipartite. And let's say KL biregular. So you know your graph looks like this. You have edges in between. On one side it's K regular, other side it's L regular. Now, it turns out that P is 1 over square root KL. Well, is this right? No, it's not quite right. It's not that P is that, but the eigenvalues of P are 1 over square root KL times the eigenvalues of A. So they scale in a predictable way. And that's not too bad to show. All right, so do we know of a regular graph which should be slow to mix? So I can tell you a regular graph which is very fast to mix, which is the complete graph. That mixes very quickly. One step, you're mixed. Okay. So the problem with the complete graph is that it's too connected. Not too connected. It's 2 as in T-O-O, not T as in the number 2. It's overly connected. So if you want things to converge slowly, you say, look, I want somehow things far apart. So do we know of a nice graph, probably very sparse, that we can talk about eigenvalues for? Cycles. Yes. Good. So if you look at the cycle, and so we'll consider our graph G, and let's do an odd cycle. The reason I don't want to do an even cycle is you run into sort of an issue with it being bipartite. It's like, well, what does it mean to converge? That's a different question. We don't want to deal with that headache. Okay, so what are the eigenvalues of A? Well, there is a 2 cosine
2 pi k divided by 2n plus 1.
Yeah, wow, good. I was worried I'd have to remember it. So k equals 0 up to 2n. That's 2n plus 1 numbers. And okay, so the eigenvalues of P. Yeah, we get rid of the 2 because it's 2 regular.
But not too regular.
It's regular enough. It's sufficiently regular. Yes, that's true. All right, yes. I see, I put myself in the corner there. It's one of those things where English has the weird sentences, like you can say, there are 3 2s in the English language. And people are like, I know what you mean. Now, write it down. I can't. What? There are things that you can say but cannot write? This is true. All right. So, and the punchline here, well, if you look at k equals 1, so you have cosine of 2 pi over 2n plus 1. In terms of n, do we know, like, what can we say about this eigenvalue? Yeah, what is it like in terms of n, approximately? Well, okay, we can do a numerical approximation. Cosine of, this is close to 0. So, okay, it's about 1. Derivative of cosine of 0 is 0. Second derivative of cosine is negative cosine. So anyways, if you do a Taylor series, so it's 1 minus x squared over 2 factorial. So it's roughly 1 minus a half 2 pi over 2n plus 1 squared. And you say, well, okay, so that's, if you look at it, that's 1 minus, we'll say order 1 over n squared. Which means it's really close to 1. And so that's bad. It means it takes a long time to mix. And especially because it's an odd cycle, you have to get all the way around to help you sort of break the curse of, like, jumping back and forth between the same states. So this just shows you it can be pretty bad when we deal with just the undirected underlying case. But it can be worse. We could have had directed underlying our graphs. And I think for directed, one of the worst case scenarios is, I'll draw something with, say, 4 states, or I guess this is 5 states? 5 states, where what happens is that at every state, you can go back to any previous state, or you can return, or you can move ahead. Well, the problem here is, yes, you can definitely get from any state to any other state. But in order for you to get from the beginning to the end, you got to kind of flip heads a lot, So it's
And each time gets harder.
right. Of course, maybe you only lose 1 step back, but maybe you go 4 steps back or 5 steps back. So in this case, it's not just polynomially close to 1; it's exponentially close to 1, and so it can be tough. So mixing is hard to do. Okay, and I will say we are going to come back to this theme before. We like eigenvalues close to 0. And your mantra is, eigenvalues close to 0, your graph is nice. Eigenvalues aren't close to 0, your graph has something going on. Now, it might be nice, but in a different way. But that's it for today.